Morning, everyone. So today we're going to be starting into our fourth main chapter. This is going to be a chapter on acids and bases, so Unit 4. You can start a fresh new page here, acids and bases. Turns out this chapter here is going to be really long, okay? So what we're going to do is we're actually going to break it up into two parts. If you're following along with the workbook here, we're going to have part 1 as sections 4.1 to 4.12. Pretty much this is going to start introducing some of the basics of acids and bases. We're going to see some definitions in today's lesson. We're going to learn how KEQ sort of rears its head again. We're going to mainly focus on strong acids and strong bases in part 1. And then what we're going to do is we're going to switch over. Part 2 of this chapter here is going to just finish up the rest of the chapter. Part 2 goes from 4.13 all the way to section 4.21. These section numbers here aren't super important. What part 2 is going to do is it's actually going to apply some of the concepts that you learned from part 1. It's going to specifically apply it to ice tables with weak things. It's going to try to solidify some of the content we did from earlier. So just bear in mind here, it's a super long chapter. Make sure you're keeping up with the material. Don't let it stack up on you because we're going to be in this chapter for quite a while. Okay? With that in mind, first part here is actually not very challenging. Again, don't really worry about these section numbers here. Part 1 is just some definitions. We're going to start off with what's referred to as the Arrhenius definition or Arrhenius theory. When I say to you acids and bases, this is probably the definition that you think about. For an Arrhenius compound to be an acid, well, acids are supposed to have an H. So an acid, it has the characteristic acid particle as an H+. Pretty much as an acid, not only do you have to have an H, you have to be an ionic compound able to actually release this H+ in solution. Usually we're going to assume that the background is water, so anything that's willing to dissociate and break off to form H+ is an Arrhenius acid. That's why we usually shorthand this one here. It has to be H something. I have to have an H to give. What about an Arrhenius base? Well, the characteristic base molecule is a hydroxide. It's an OH minus. And in a similar fashion here, it should be a compound that already has an OH. We need to modify that in the upcoming lessons. But pretty much, if this chemical here has an OH and you manage to release this OH minus in solution, that's what actually makes you a base. So I'm just going to say BOH, where that B can be anything, and AOH, lithium hydroxide, whatever you want, right? So that's the Arrhenius definition. That's the definition that we know, okay? I'm going to just show you an example of this one here. HCl is hydrochloric acid. You would have called it hydrogen chloride. This is actually our stomach acid. It's an ionic compound, so it gets ripped apart. This one ends up becoming H+ and Cl-, okay? So the chemical that ends up doing this is the reactant. So that's the Arrhenius acid. In a similar way here for base, if I have NaOH here, it also breaks up to become Na+ and OH-, okay? This one here dissociates. It's the reactant involved that releases off the hydroxide, so therefore it is a base. There are some chemicals that don't manage to actually release it off. So if you remember back in Chem 11, we may have a compound like CH3OH. That was an OH grouping, but because it was covalently bonded to the carbon, that actually doesn't get removed. So methanol is actually not considered a base. We had considered that an alcohol family. It has to be able to release and get rid of this OH-. Unfortunately, this Arrhenius definition is a little bit too restrictive. It's a little bit too zoomed in for my liking. Because there are chemicals, we know ammonia has basic properties. It's going to knock the pH bigger than 7, it's going to be a nice cleaning agent, it's going to taste bitter, and yet I don't really see how ammonia can actually release off hydroxide. So ammonia right now here is just a question mark. How is ammonia supposed to be base? It will later on release hydroxide, but definitely it doesn't have the hydroxide with it. So how is that possible? Acids and bases, they participate in a very simple reaction called the neutralization reaction. A neutralization is a special case of a double replacement reaction that involves an acid reacts with a base, and this one here, one-way arrows, ends up forming a salt and then a water. That word salt doesn't necessarily mean table salt. The salt here just means some generic ionic compound. It's basically going to be the leftover whatever parts were remaining. So, for example, for the acid might be, let's go HCl. Let's react with NaOH. Again, back in Chem 11, I would have asked you, well, predict, balance, and classify. Well, because this is a compound and a compound, and what's actually happening here is we actually have an acid reacting with a base, we're going to basically, the hydrogen switches place with the sodium, so we end up getting sodium chloride. This time it actually is table salt. That's very rare. And then what's going to happen is the H, having swapped places with the Na, H is going to be bonded with OH and forming HO. Okay? Well, what's HO? Okay? Well, this HO here is actually two H's and an O, so that's actually what we refer to as water. Okay? In fact, all neutralizations, it's the acid's job to give you an H+, it's the base's job to give you an OH-. We're going to see an equation of this later on. These actually react in a 1-to-1 ratio. The net ionic equation is 1H+ reacts 1OH- and ends up forming 1 water. The leftover salt here is just what's remaining out of the switch. Okay? We can actually use that to our advantage here, just to show you why it's not always going to be table salt. Let's start off with H3PO4, so phosphoric acid. Let's react it with strontium hydroxide. Same question. Predict, balance, classify. Okay? So what you can do is you can say, well, it's the acid's job to give an H. Just one molecule of this would give 3 H's. One molecule of the SROH2 only gives you 2 H's. That's not going to be an even ratio. What do both 3 and 2 go into? Well, they both go into 6. Let's double this, and let's triple the other one. I would overall have 6 H pluses. In this case here, I would get 6 OH minuses. How many waters would I end up getting? I would get 6 waters. Sometimes I prefer to write it as whole like this, so that way you can actually count. Well, 6 H's, so those are the 2 times 3 there, and I have 6 of the OH as well, and that's the 3 times 2 there. Sometimes it's hard when you actually write it as 6 waters because those hydrogens are sort of condensed on you there. Okay? With the exception of those 6 waters, what's the remaining compound? Well, they're going to switch partners, so strontium is going to be bonded with phosphate. You do still need to check that you've written the correct compound. Strontium is an alkaline earth metal, so +2. Phosphate is a -3, so I would actually need SR3PO42. At that point there, it should already be balanced. Okay? So neutralizations here should always be really easy to balance because it's the H+, it cancels out the OH- in a 1-to-1 ratio. Okay? That's section 1. Okay? Really short section. 4.2, also similarly short here. They just want to introduce to you some common acids and bases. Right? Some things that we might see in everyday life. Okay? I already mentioned to you here, hydrochloric acid is actually what our stomachs use to actually digest food. So that's going to be HCl. That's a binary acid. Sulfuric acid. Sulfuric can be spelled with either a pH or an F, doesn't matter. Sulfuric acid is used in our car batteries. It's used as a really strong acid, as a catalyst for many reactions as well. That's common as well. Maybe I should write this down for you here. So HCl is our stomach acid. The pH of stomach acid is actually fairly low. That can actually burn holes in our stomach. Fortunately for us, we have a mucus lining inside our stomach that actually keeps it from touching our stomach tissue. People that you know of may have ulcers. That's places where the mucus lining had actually wear thin, and basically the acid was starting to react with some of the sides of the stomach. When the food gets digested, it gets tossed into the small intestine. That's when other organs like the pancreas, gallbladder, things like that, they throw in a lot of buffers to neutralize the acidity to make sure it doesn't cause any permanent damage later on. Sulfuric acid, like I mentioned, basically all our car batteries need sulfuric acid to run. Nitric acid here, these are just some common acids. Nitric acid would be HNO3. Probably more so what I want to introduce to you, again, is just sort of the naming of acids. If there is still hydro in the name, it's probably just a binary acid. It's probably like a 2-part acid. So it's just H with the chlorine part. If I have lost the hydro, I still know it's an acid, so I still know you have to have an H. But if it has an ic ending, it's going to be the ATE, so sulfate nitrate. If it's an OUS, sulfurous acid, it's going to be SO3 instead. Okay? There's another acid that's really common here. We can call it acetic acid or ethanoic acid. This one here, pretty much I've just asked you to memorize. This one here is chiku. Okay? Chiku is actually an organic acid. It's actually a very special type of acid. The chiku is actually a carbon bonded to 3 H's. This Ku part actually is a carboxylic acid or a carboxyl group. That Ku part always means carbon. Double bond to an oxygen, single bond to O, single bond to H. Okay? So that's what that functionality tells you. Normally you'd say, wait a second, this is an OH. Shouldn't it be a base? This is exactly the same OH that bases have, but again, you don't just have to have OH, you have to be able to release this OH in solution. Turns out, because this one here is a covalent bond, just like the methanol we saw earlier, water has trouble breaking apart this compound here. Water has no trouble, though, breaking apart off the H. The H leaves as an H+, and we end up having just the acetate. It has resonance. It actually adds a little bit of stability. It actually allows it to form a little bit easier. But there we go. We've released an H+, so we're definitely acetic acid. A very dilute sample of acetic acid is vinegar, so 4%, 5% acetic acid is what we use for the soured compound. For bases here, some other common ones we have are sodium hydroxide. We already saw that in our neutralization equation. The one that they always like asking is which base is used for drain cleaner. That's this one. Okay, so just if you want to just recognize it for yourself, the one that's used in drain cleaners is sodium hydroxide. It's NaOH. There are other bases as well, not as fancy in terms of the naming. So we can do, say, potassium hydroxide. Pretty much anything with a hydroxide is going to be a base, so like KOH. Though ammonia, like we had just memorized the compound, it was NH3, we still need to come back and we still need to figure out, well, how is ammonia is actually a base? So that's just a listing of some common acids and common bases. Let's take a look at some common properties that these have. So common chemical traits. Although I'm not encouraging you to taste these ones here, some things that they have in common. Sorry, let's just do the taste first. So acids, they tend to taste sour, like I mentioned with the vinegar. Bases, they tend to taste bitter. So that's one way of differentiating them. We typically will use a lot of different indicators and different meters to actually figure out sort of which side we're on. One really common scale here we're going to look at later on is called a pH meter or a pH ruler. We are going to do all the math to actually figure out the pH, but I want you to track here, pH is just the name for the ruler. Usually 7 is the dividing line. That 7 here is actually neutral only at 25 degrees. If we're not at 25 degrees, the dividing line actually pushes beyond. The acid is actually going to be small on this pH scale. So as I go pH 6, pH 5, pH 4, we're actually getting more acidic as you head towards the side. Usually we ballpark at around 0 and 14. You can get to negative pH, you can get beyond 14. It's just going to be harder and harder because what we're going to learn in an upcoming lesson is the pH is in a logarithmic scale. So basically every step is actually 10 times as harder than the step before it. The only logarithmic scale I think you've seen is the Richter scale. So if I have an earthquake of magnitude 5, it's 10 times stronger than 4. An earthquake of magnitude 6 is 10 times stronger than the 5. It's 100 times stronger than the 4. It's getting increasingly hard to push really far past this neutral line here. Just a little trick in wording here. As I get smaller and smaller, I would say pH is decreasing, right? I'm going from 7 to 6 to 5 to 4. pH decreasing actually implies we're getting more acidic because we're getting to the acid side. Sometimes people think, oh, pH, oh, it's an acid scale. You're watching H+. Acidity decreases, oh, less acidic. No, this actually means the pH number is actually dropping. And as that number drops, we run towards the acidic side. In contrast here, if I have pH increases, right? Yes, we are going to watch H+, but as the pH increases, I'm actually climbing towards the basic side. pH increases actually implies the thing is getting more basic. Okay, so just watch out for that terminology there. pH increases is one way of saying more basic or less acidic. Okay. Towards the end of part 2 of this chapter, so way after, we're going to take a look at many different indicators. I'll introduce one of them here. We've used phenolphthalein in the past. It's colorless in acid and it's pink in base. I can use litmus as an indicator. Sometimes we actually borrow that in our English language. We say, well, what's the litmus test for something? Turns out for a litmus test, the solutions for litmus are actually red in acid, and it's actually blue in base. Now, the thing that confuses people here is litmus can be prepared in the neutral form. It's actually sort of whitish. It's neither red nor blue. It can be prepared as red litmus. It can be a piece of paper. Basically, I have litmus in the red form already. Oh, the paper looks red. I don't really care about the starting color. What I care is when you dip a strip of this litmus paper here into a water solution, if the solution happens to be acidic, because it's supposed to be red in acid, this red litmus will just stay as a red color, right? if the solution was actually absorbed here as a blue color to begin with, so it's blue litmus. Ooh, big difference. Well, a blue litmus here, if you stick it into the same acid solution, because litmus as a chemical is supposed to show red in acid, because I'm starting out blue here, I dunk this blue piece of paper inside. The top part that's not touching the acid will stay blue, but the part that's actually touching the acid will actually switch over to red. So this is actually one good way of identifying acids and bases. Use corresponding indicators. Litmus is a very common one. Okay. Some other properties here that are specific to either side. We'll just end off with this here. For an acid, these acids are known to react with metals to produce hydrogen. And that hydrogen here will actually be a gas, so that's actually going to be bubbles. Hopefully by now we've done a few reactions. If you drop a piece of zinc into HCl, well, pretty much what I'm proposing to you here is a single replacement reaction. We would check our pink sheet and we'd say, well, zinc, yep, zinc is more active. Zinc has no trouble kicking off the acid. Zinc is going to switch partners. It's going to become zinc with chlorine, ZnCl2. When hydrogen gets kicked off, it's H2, but that's a gas that's formed underwater, so we're actually going to see bubbles end up forming. Most often when we actually deal with acids, it's going to be heavily diluted. The reactions are not going to be crazy fast, but definitely this property of reacting with metals to produce these bubbles of hydrogens, you can pop the hydrogen afterwards if you like. It's specific for acids. Both of these are actually corrosive, so definitely acids, don't accidentally splash it on yourself here. If you do, rinse it off with water right away. Bases are also going to be corrosive. And I'm also going to give you one last property here for a base. These ones here typically end up feeling slippery. That's why we use them for a lot of different soaps. So liquids are already, they already take the shape of the container, things like that. But if you accidentally spill some, like let's say NaOH on your hand here, your hand will feel extra slippery. So in this lesson, I just wanted to introduce to you the chapter on acids and bases, teach you this sort of Arrhenius definition. In tomorrow's class, we're going to take a look at what is the actual nature of an H+. It actually is going to actually be a proton, and that's actually going to give us another definition called the Bronsted-Lowry definition. Okay, but we'll leave it off there. Your questions would just be practicing some neutralizations, identifying some common traits for acids and bases. All right? If you have any questions, just let me know. Thanks, guys.